just as a review, we have gone over density, we have gone over not combining ratios yet. We're going to go over isotopic symbols today. We're going to talk a little bit of the periodic table today, and we haven't done molecular weight, we haven't done average atomic mass, we've gone over sig figs, we've gone over accuracy and precision. So today we're going, I guess in this video, we're going to be going over the isotopic symbols and touch a little bit on the periodic table. Okay, so first thing to look at is, what is an isotopic symbol? Isotopic symbol. So we use an isotopic symbol to tell us exactly what an element is. We can get from the isotopic symbol, we can get what the number of protons are, what the number of neutrons are, things like that. This is something that I do suggest possibly putting on your 3x5 because I'm not good at memorizing where things go. I'm like the worst with that. So this kind of has to do with that. So I'll show you an example of an isotopic symbol. So we'll look at sodium, right? We'll look at sodium with a charge of +1 because that's the charge that sodium usually takes on, which we'll talk about in a minute. And then up top here is going to be the mass number. Now, I don't know the mass of sodium, so let's look it up. Mass, or molecular AMU of sodium. 2.98, so I'm just going to put 23 up there as the mass number, and then the atomic number, which is the number of protons, and I'm pretty sure it's 11. Yeah, I'm 99% sure it's 11, so I'm going to keep that there because I feel pretty confident in that. And basically what we can get out of this is the number of protons, the number of electrons, and the number of neutrons. So we use these in order to tell us all of this information, which I'm sure this may become a test question. So either he's going to give us these values and we're going to make an isotopic symbol, or he's going to give us the isotopic symbol and we are going to have to figure out the number of protons, number of electrons, and the number of neutrons. Okay, so with that being said, let's talk about this charge here, right? So a charge of +1 doesn't mean you're adding on an electron. It actually means that you're subtracting an electron. So sodium should have 11 electrons if it was neutral. And you're probably like, Grace, did you pull that number out of, you know where? No, I didn't pull it out of you know where. This number here is the number of protons. And then this is the mass, so let me write that up there. So this is the mass, usually in AMU, atomic mass units is what they call it. And then this is the number of protons. Wow, that is... Prons, it's the number of prons. Protons, there we go, I must have forgotten yeah. Anyways, so the reason why it should have 11 electrons is because protons are positive and electrons are negative. In order to make it neutral, to make, think of it like a magnet, or even just like a math problem. Say we have 11 protons minus x plus x equals 0. What number needs to be here? Minus 11. So because electrons have a negative charge, we need 11 of them. So we should have 11 electrons, right? So 11 electrons would look like minus 11, and that's to make it neutral, right? So with 11 electrons, we have a neutral charge. If we were to add on an electron, we would say plus minus 1 because it has a negative charge, and that element will become -1. But in this case, sodium is a metal, so it tends to lose electrons, which we will talk about, why that happens and how we can see that on the periodic table. It tends to lose electrons, right? So we're going to do -1, which for those of you who don't know would just become a plus. So 0 plus 1 is equal to +1. And you want to have that +1 there because that tells us that it's a positive, because, putting just 1 at the top is kind of like, is that a +1 or a -1? We won't know. So we always like to add that in there just to keep us in the loop. Okay, so I'm going to do an example of how we can determine all of those things that I just said before from that you know, what we're given there, right? So let's do the example of lithium. Also going to give it a charge of +1 because that's usually what it tends to take on. The mass of it should be 6. I'm going to double check that actually. AMU of lithium, unless it usually lithium. Let's see. Okay, 6.94. So usually it has a extra neutron in there. Oh my god, I just deleted my sketch pad. Oh, that's okay. Okay, it stayed. Cool. So, oh man, but I can't go back now. Okay, we're gonna make that 7. Sorry to everybody here who has OCD. I'm not erasing the whole thing because I don't know how to erase on this stupid app. Oh my god, there's literally a dabbing unicorn. Bye. Okay. So lithium, that's the mass, and then down here the number of protons, which is 3. So let's say that we're just given this, and we're asked what's the number of protons, the number of neutrons, and the number of electrons with this isotopic symbol. So first thing that we're going to do, right, is we're going to look at the number of protons because that's the easiest. The number of protons is always going to be on that left-hand corner there, right here, bottom left. That's always going to be the number of protons right there. 3, easy, cool. Moving on to the next thing, neutrons. So the number of neutrons is always going to be equal to the mass number minus the number of protons, right? The reason being is because neutrons usually have a mass unit of 1. Protons usually have a mass unit of 1. So if you take, 2 minus 1, you're going to get 1. But basically, it just works because that's how mass works. The whole thing, as probably Professor Sherlock would say, the whole enchilada minus a little bit of an enchilada will give you the rest of the enchilada, whatever. I'm literally turning into Professor Sherlock, I swear. So we do 7 minus 3, which will give us 4. That's the number of neutrons. Now looking at electrons, what we do for electrons, so the number of electrons, is going to be equal to the neutral, and we're going to do minus, I want to say, the charge. Yeah, minus the charge, right? So the charge is +1, so the number of electrons is equal to neutral, so the neutral point would be 3 electrons because we have 3 protons. Minus 1 is going to be equal to 2. Number of electrons, 2. Cool. I'm going to do an example now of something that would have a negative charge. Okay, so something that would have a negative charge. Let's look at something like chlorine. Chlorine's always a good one to do. We like chlorine. Chlorine, I know the mass number is like 35. It has 17. Don't ask me how I know all this stuff off the top of my head, but I do. And it's quite embarrassing, I would say. So we're looking at the number of protons, number of neutrons, and the number of electrons. Okay, number of protons. Easy, right? We're doing that same process from before. We're just looking at this number here and we're saying, hell yeah, that was easy. We got 17 protons. Next step, to get the number of neutrons, we take the mass of 35 and subtract that from 17, which I need a calculator for that because my mental math has ran out. Okay, so neutrons is equal to 18. Let's put that down here. And then the number of electrons. So the number of electrons is equal to the neutral point, which would be 17, because 17 minus 17 is 0, minus -1. So minus -1 because it becomes a positive. So we're going to have 18 electrons, and there is our final answer. Yippee. Okay, so now, the age-old question. How the hell do you know that chlorine is going to lose 1 electron? Where did you get that from? And how can we figure that out? So, Reason why this happens is because any element, write any element here, any element, they want to have an outer shell of 8, because guess what happens when you have 8 electrons on your valence shell? They're lazy and they do nothing. They literally just sit there. They float around. They chill out. That's why we have the things called noble gases. The reason why they're called noble gases is because they literally don't do anything. They don't react with anything. They just chill out. They're calm. They don't do anything. They don't explode when they're exposed to water like sodium does. Sodium will literally explode if you expose it to water, like because it doesn't have that octet. So everybody wants to get to this octet. They're like, yes, let's get to 8 outer shell electrons. This is awesome. This is exactly what we want. But most of them don't have that. So what they do is that they either lose electrons or gain electrons. That's their goal. They want to lose electrons or gain electrons. So let's go over why something would lose electrons and why something would gain electrons. So what I have pulled up here is the periodic table we're going to be using for like the whole class, because it's elements. So let's look at something like sodium, right? Sodium would have 1 outer shell electron, and again, you're probably like, how do you know that? The outer shell electrons is the p group. So you might remember this from high school, this is the s group. So it's the s group plus the p group, right? Here's our s group. These 2 columns here. 1s, or whatever number S1, whatever number S2, and the p group. So we add those 2 together, and that's how we get the number of electrons. So let's look at something like sulfur, right? You're probably like, how many electrons does sulfur has on its outer shell? So you go here. 1, 2, 3, 4, 5, 6. It has 6 outer shell electrons. Something like strontium. 1, 2. It has 2 outer shell electrons. Now let's look at something like acetine. 1, 2. Skipping these because they're not in the p or the s group. 3, 4, 5, 6, 7. 7 outer shell electrons. So with that being said, once you know how many outer shell electrons, it's really pretty simple in order to predict what's going to happen, right? So as I said before, they're either going to gain or lose electrons. So let's talk about why they do one or the other. So right, we're going to gain or lose. Okay, so let's look at something like magnesium. And let's see how many outer shell electrons it has. It has 2, right? Starting here, 1, 2. Easy. That's easy to draw. This is all just for a visual, so you don't have to necessarily know how to do this, but it's very helpful in order to see, right? So it has 2 outer shell electrons. Now, in order to reach 8 valence shell electrons, either it could shed this whole thing. It can get rid of this whole energy group, leaving it with its bottom valence shell electrons. So down here it also has 8, because if we look here, its first energy group is filled, so it's second energy group technically. So it's 1, 2, 3, 4, 5, 6, 7, 8. So the bottom shell's happy. They also have nothing to worry about. Like they're chilling down at the bottom. So you can either lose 2 electrons, or it can gain 6 electrons. What do you think is easier for an element to do? Do you think it's easier for it to just say, screw these electrons, we're just gonna pop those off? Or do you think it's gonna take more energy to grab 6 electrons from somewhere random, go like 1, 2, 3, 4, 5, 6? That takes way more effort. So this element's gonna be like, screw that option. No. We're gonna lose 2 electrons because that's a lot easier for me to reach my octet. So the charge of this one will become positive 2 because you're losing 2 negatively charged things, meaning it's going to bear a positive charge. So magnesium is most likely to get a charge of positive 2. Now let's look at something where it would gain a negative charge. So let's look at selenium. That one will be fun. So let's look at how many electrons it has now. So it has 1, 2, skipping the D block, 3, 4, 5, 6 electrons. So let's draw that out. Selenium. 1, 2, 3, 4, 5, 6. Alright, so same thing as before. Either it can shed all of these outer shell electrons, leaving the inner, which also has 8, or what it can do is that it could just gain 2 electrons. So again, let's think about it. So it can either lose 6 electrons or gain 2 electrons in order to get to its happy octet. Which one seems easier? Getting rid of all these, taking all that time to say, yeah, screw these electrons, getting rid of you? Or is it going to be more easy for it to gain 2 electrons? So that's why it does this. Gains 2 electrons because it's easier. So selenium is going to bear a -2 charge because you're adding on 2 negatively charged things. Another way that you can think of it, if you remember this, this block here is called the stairs. So these are things that are semi-metals. The definition of a metal is something that will lose electrons, right, in order to get a happy octet. So if you're looking at something like acetine, it actually is most likely going to lose the electrons. And that's just because acetine is so massive to the point that it's really easy for it to lose electrons, which, again, we'll probably talk about in a different section. But it's a very, very massive element. So it's going to lose those electrons easily because they're so far away from the positively charged center. Again, you can think of it like a magnet. But if we're looking at something like fluorine, it's really small. So the electrons are really, really close to that positively charged thing. So it's really easy for it to gain an electron. But what I'm getting at here is that if you go across this, anything to the right is going to gain electrons. So everything that's blue here, these all gain electrons. They're more likely to gain them. So they're more likely to bear a negative charge. But if we go all the way over here into this, including the transition metals and including these, they're all going to bear a positive charge, right? So that's just something that you can keep in mind also when you're doing chemical reactions and when we get to that unit. That's always a good thing to know. Okay, so I think that might cover kind of everything that I wanted to go over today, but we'll just do some practice. We'll do 1, 2, 3, 4, 5. I'm gonna add in 2 practice in here that we can do to kind of show. So we'll do protons, neutrons. I'm gonna add some practice in there talking about charges and stuff so that you guys can get some practice in there with that because it is kind of applicable in what we're doing. Okay, sodium we'll do. Lithium. I know these are examples that I already showed, but I think these are, fairly easy ones, so you don't have to sit there for like an hour trying to do some math. 3. Let's think. We'll do carbon. Yeah, we'll do some carbon. Carbon. What is carbon's weight? Go to the periodic table to figure that out. Oh my god, they don't have it on here. Oh, yes, they do. Okay, 12. Alright, carbon's 12, and I want to say it's number 8. No, it's 6. For somebody who took organic chemistry, I don't know. Okay. Protons, neutrons, electrons. And then let's look at doing the charges, right? So what will be the charge of... you guys also will probably need a periodic table to do these. So what will be the charge of calcium as an ion? And then we'll also do phosphorus as an ion. Okay, so just as before, you guys can pause the video if you would like to, because I will be explaining it now. Okay, so number 1, first thing we always want to do is protons because that's easy. We don't have to worry about that. The next thing is doing neutrons, which is the mass minus the protons. So 23 minus 11. This is also embarrassing. I cannot do that math in my head. 12 neutrons. All right, and then the number of electrons To keep it neutral, we know it needs to have 11, but it has a charge of +1, so we know that it's going to have 10 electrons because we are removing something negative, making it a positive charge. Okay, protons here. We're going to have 3, neutrons, 4. Didn't have to do the calculator on that one. And then the number of electrons we're going to have is 2, because to keep it neutral, we need 3. But you're removing one of those, making a positive charge, so 3 minus 1 is 2. Okay, protons here, we have 6, number down here. Neutrons will also be 6, because 12 minus 6 is 6. And the number of electrons that we have, so to keep it neutral, there's 6, but we're adding on 4 electrons, so 10. 10 electrons. Cool. Alright, so now to do this one. Calcium. What is calcium going to do? Let's look over at calcium. In order to get to an 8 octet, it needs to remove 1, 2 electrons, right? 2 electrons. So, oops. We're removing 2 electrons, so we're going to get a charge of +2. And then protons. Protons. Phosphorus. I'm looking at P and I was like, that means protons. No, it doesn't. It can, I guess. So phosphorus. How far away is it from an octet? So it's 1, 2, 3 away from an octet. So it's going to bear a charge of -3 because it's most likely to lose those electrons because it is a non-metal, or you can also think of it, it's a lot easier to lose 3 electrons than it is for it to gain 1, 2, 3, 4. It's another way of thinking of it. Okay, so there's the answers to those questions. I hope that this video is somewhat helpful. This was kind of a long one, and there's like a lot of concepts thrown there, but hopefully it is helpful to know that. So yeah.